space seems to us like an empty and dark void. Yet, the Milky Way is filled with countless numbers of diverse objects from barely noticeable asteroids to giant star clusters. Each of these celestial bodies is unique in its own way, but in some cases, a combination of chance and the laws of nature gives rise to truly strange and anomalous structures. And that means it is time to embark on another fantastic journey into the depths of boundless space. First, we will travel hundreds of light years to reach a truly remarkable cosmic object, a unique double pulsar, which is a direct embodiment of the laws of relativity. Then, we face a long flight through the immediate neighborhood of the solar system in search of the strangest cosmic structures and anomalies. Next, our path will lead us to some of the most unusual and sometimes even terrifying exoplanets that astronomers have managed to discover so far. After that, we will visit several of the most hospitable and Earth-like worlds that could hypothetically harbor life. And finally, we will cross hundreds of light years to break beyond the boundaries of our galaxy and plunge into the bottomless darkness of giant voids, supervoids. Get ready. We are about to begin. For a number of reasons, neutron stars. First of all, celestial bodies of this class are incredibly rare. According to calculations, for every 1,000 there is only one such object. Secondly, they are very compact and emit almost no light in the optical spectrum. Therefore, before the advent of X-ray telescopes, spotting these objects was virtually impossible. Unsurprisingly, the first neutron star was discovered only in 1967, several decades after their existence was theoretically proposed. In many ways, this was facilitated by an unusual phenomenon to the law of conservation of angular momentum. Thanks to this effect, most neutron stars have a very high rotation speed, and the interaction of their magnetic and electric fields generates powerful bursts of radiation, repeating with a very precise regularity. Such objects are called pulsars, and they make up the majority of neutron stars discovered. Date 2. Their pulses are effectively captured by X-ray telescopes, even at a distance of thousands of light years. In total, more than 3,000 stars have already been discovered, with about 90% of them being isolated, solitary objects, while the rest are part of binary and multiple systems.
Чаще всего
the companion of these cosmic bodies is a red giant or a main sequence. This happens when two similar stars synchronously approach the end of their life cycles, and the explosion of one triggers the collapse of the second. Due to the loss of energy during this transformation, the remnants of the stellar cores draw close together to a very short distance, causing their relative orbital velocity to increase to immense values. And this is precisely how, according to modern concepts, an amazing system called PSR J0737-3039 was formed. It is located at a distance of about 4,500 light years from Earth and is unique in that it consists of two pulsars once positioned very close to one another. The first of them is 34% more massive than the Sun and features an incredible speed of self-rotation. Every second, the object completes 44 revolutions around its axis. The second pulsar is slightly smaller and slower. Its mass is 1.5 times that of the Sun, and its rotation period is 2.77 seconds. If we want to take a closer look at these objects, we will find that their sizes are extremely small by cosmic standards. The diameter of each companion in the system is no more than a couple of dozen kilometers, which cannot be said about their mass, which is comparable to most known stars. The consequence of these factors is the staggeringly high density of the matter of which the pulsars are composed. And to understand this matter, we need to look deep into their interiors. The use of mathematical modeling methods combined with the theory of neutron star structure allows us to learn even what is hidden from direct sight. The outermost layer of objects of this class is the atmosphere. However, for neutron stars, this concept is significantly different from the planetary gas envelope we are used to, like on Venus or Earth. For both components of the system we are examining, this layer is no more than a few millimeters thick. This situation is typical for the absolute majority of neutron stars. However, the youngest and hottest objects of this class can have an atmosphere spanning several dozen centimeters. It consists of plasma highly ionized, remnants of stellar matter. Mainly, these are hydrogen and helium, but heavier elements are also found. The next layer is the outer crust, the thickness of which can reach several hundred meters. Gravity in this region is not strong enough to overcome the electrostatic repulsion between electrons and protons, yet it is sufficient to crush the conventional structure of matter. Elementary particles are mixed together here, but they still maintain their internal integrity. Several powerful forces act on the outer crust at once, such as gravity, the magnetic field, electrostatic repulsion, and centrifugal inertia. Due to their combination, the surface of neutron stars is under constant mechanical stress. Periodically, it ruptures in the form of starquakes, titanic deformations of the celestial object surface. As a result, mountains a few millimeters high and cracks up to a centimeter wide form on it. These figures seem insignificant, however, under conditions of extreme gravity, a centimeter high mountain is analogous to Mount Olympus on Mars. If we descend even further, we will see that this layer has no clear boundaries and extends into the depths of the neutron star for several kilometers. As we dive deeper into its interior, the pressure gradually builds up, forcing more and more electrons into atomic nuclei, initiating a reaction with protons. As a result, a neutron is formed, along with elusive particles called neutrinos, which almost immediately escape the celestial body's interior, carrying away excess energy. In turn, beneath the inner crust lies the outer core, composed entirely of neutron matter. This remarkable substance consists of a multitude of tightly compressed neutrons, and its density is 10 to 15 times higher than that of an atomic nucleus. For example, our planet, if compressed to the, would have a radius of only 150 meters, and a cubic centimeter of its volume would hold several billion tons of neutron matter. Matter in both components of the system we are considering. The outer core extends to the very center of the object, but particularly massive neutron stars, according to modern views, also possess an inner core. Its structure remains a subject of scientific debate. According to one hypothesis, the pressure at the center of massive stars can be so immense that it can dissolve even the neutrons, forming a hypothetical quark matter. Such an object is called a quark star. Other assumptions allow for the formation of hyperonic or chaotic cores, consisting of exotic matter with highly unusual properties. However, all these fascinating structures remain of hypotheses, and proving or disproving their existence is currently impossible. If we examine the system as a whole, we will uncover several surprising and intriguing facts. First and foremost, it can be noted that, according to calculations, the pulsars in this system travel rapidly around a common center of mass, along moderately elongated and highly compact orbits. Observations indicate that the average distance between the components is just 800,000 kilometers, which is nearly half the diameter of our Sun. Due to such a short distance, the velocity of both objects is extremely high. It exceeds 300 kilometers per second, allowing the pulsars to complete a full orbit around their common center of mass in just 2.45 hours. Such rapid motion gives rise to a series of unusual phenomena driven by the effects of the theory of relativity. For instance, observations reveal that at the pulsar's closest approach, the self-rotation period of each of them temporarily increases by 0.38 milliseconds before returning to its original values. This effect cannot be explained from the standpoint of classical physics, yet the theory of relativity predicted it long before its practical detection. This anomaly is related to relativistic time dilation, which becomes strongest precisely at the moment of the object's closest approach. Another highly noticeable phenomenon manifests during eclipses and is linked to an anomalous gravitational redshift captured in the spectrum of one of the pulsars. The fact is that the gravity of the closer to us slows down the signal passing by from the distant object. Because of this, the radiation loses energy and its wavelength increases. It is also known that the orbits of these celestial bodies are influenced by their interaction. This is expressed by the fact that their closest approach, known as the periastron, is constantly shifting. This phenomenon is called relativistic precession and has long been known to astronomers. Usually, it is detected when studying fast-moving celestial bodies. For example, Mercury's orbit shifts by 43 every 100 years. However, the periastron of this binary pulsar shifts 140,000 times faster over the course of a single year from its previous position by a whopping 17 degrees. Thus, among all known stellar systems, PSR J0737-3039 possesses the highest relativistic precession. If we step away from dry numbers and ponder about hypothetical planets that might be hiding within this amazing system, their existence is considered unlikely, but still possible. Some objects far removed from the center hypothetically stood a chance of surviving the devastating double supernova explosion, while others could have formed much later. The answer to this question is complicated. None of the widespread methods for finding exoplanets are effective for studying systems like this. In any case, there is no talking about the habitability of hypothetical celestial bodies in this freezing cold and lethal radiation make them extremely inhospitable environments. Observations show that this binary pulsar constantly generates gravitational waves, causing the distance between its components to steadily decrease by 7 millimeters every single day. This phenomenon occurs in all physically bound multiple star systems, but it is usually too faint to be reliably measured. This tells us that, in roughly 85 million years, the pulsars will merge together, forming a black hole. This epic cataclysm will become a source of ultra-powerful gravitational waves, which will ripple through the entire Milky Way and reach other galaxies far beyond its borders, and the flare accompanying the merger might briefly become one of the brightest stars in any case, the echo of this devastating explosion will eventually fade without a trace into the infinity of the universe.